Hi, this is Sabir again. So in this lecture, I'm going to discuss all about the orthogonal tensors, so how we can use that. So here the over orthogonal tensor, right? Yep. So how we can use that orthogonal tensor? So from the name, it is pretty obvious that what is that. Orthogonal tensor is nothing but is a tensor, is a linear transformation under which the transformed vectors preserves their length and angle. That means if we consider orthogonal tensor, for example, here Q, this orthogonal tensor that will transform two vectors, three vectors, or whatever the number of vectors, but it will preserve their original length and the angle among them or between them, right? So for example, here we have arbitrary vectors here A and arbitrary vectors B, right? So if q is the orthogonal tensor, right? Q is the orthogonal tensor. So if q transfer a, say for example q transform a, then it will transform a new vector that will have a length as is previous. Say a, then its length would be the same, equal to its previous, and its angle would be the same. So similarly, qb equal to b, right? So orthogonal tensors are nothing but under which the transform vectors preserves their length and angle, right? Okay, so and their angle, so cos a b is same, equal to the um, cos transformed here, right? Yeah. So the angle between A and B is same after transformation QA or QB, something like that, right? So for any kind of vectors, here we have shown here example here A and B. So for example, here I can give you an example. Say this is vector A, right, and this is another vector B. So it has its own length or something like that, and it has its theta, something like that. So it will be transformed, there will be another vector that will transform. Say for example, it transforms something like that way, but the length, say for example here A and B, so B and their angle would be the same, something like that, right? So their angle and their length would be preserved, something like that. Since A and B are arbitrary, so we can write down here. So from the definition of transpose or something like that, we know that q qt and q equal to identity, right? This is a uh, orthogonal tensor here. So from the definition of transpose, we know all about that. So this means that for an orthogonal tensor, the inverse is simply the transpose, right? So the inverse is simply the transpose. So if you want to find out the qt, so then I divided by the q would be the inverse of q, right? So qt is simply the inverse of is, right? Right. So this means that for an orthogonal tensor, the inverse is simply the transpose. This is nothing, but it's very easy, right? Yeah. So we can write down here q p q or q q to the transpose equal to I, right? That is very easy. So in matrix notation, in matrix notation, you can write down this here in similar form. Say q t q equal to q, sorry, so yeah, q and qt is equal to the same as the inverse identity matrix or something like that, right? So in the subscript notation, we can write down here, say q here, m I, and q m j in transpose, something like that. So you write down q I m q jm equal to the identity matrix or Kronecker delta, something in subscript notation or something like that, right? So this is all about the orthogonal tensor or something like that. There are a lot of examples here in the book in Introduction to Quantum Mechanics. I recommend you to go through this and to solve all of this. So it's very easy. So we can do that easily. So for example, we can give you an example here. Say for example here, say t is a vector. Say t is a t is a vector. Say minus one. Say minus one 0 and 0, say 0 1 0 0 0 and 1. So it's a vector, right? So its transpose is, so I'm going to so its t transpose is something like that, minus 1. Transpose is the same, right? Yeah. So 0 1 0, so 0 0 and 1. So yes, if it is something like that, then if we write something like this way, multiply this t and t transpose, then we'll get 1 identity matrix 0 0. So 0 1 0 0 0 and 1, right? Yep. So it's pretty easy. The determinant of t is something like, if we calculate determinant, then determinant will be the minus 1. Determinant t equal to the minus 1, something like that. So it's very easy and pretty obvious, pretty all of that. So it's very easy. So there are several complicated problem over there. So we can do the determinant of the matrix of any orthogonal tensor Q is easily shown to be equal to either plus 1 or minus 1. In fact, since we know right here Q matrix and Q to the power transpose, Q transpose, sorry, Q to the power transpose is I, right? So therefore we can write down here, say, so from here we can write down the length or something like that. So Q uh, matrix Q, yep, Q transpose, right? Yep. So we can the length or absolute value or something like that. Then we can find here the Q absolute value and Q transpose absolute value uh, equal to identity matrix or something like that. Yep, identity matrix. So now we know. So the absolute value, if you take the absolute value, then definitely from this you can take this here. Q absolute value of that equal to Q to the power transpose, right? Yeah, and we know I absolute value of I equal to 1. So therefore Q absolute value square equal to 1. Thus we can write down Q absolute value equal to plus minus 1. Determinant of a determinant of any orthogonal tensor Q is easily shown to be equal to either plus 1 or minus 1, something like that. So it's very easy, right? So there are several examples in the book, so I recommend to go through that. Okay. So thank you very much with the lecture, and I'm going to show you then on the next lecture about the symmetric and asymmetric part of a tensor. It is very important for that. Thank you very much.